So here's our situation. We have the parallel rays coming in, the one ray at a distance delta x from the central ray, refracted at the angle delta x over 1.33 r. Again, remember that's measured in radians. So we have theta I, and I haven't written down what theta I is. Let's write that down. That's approximately just delta x over r. And theta r, which is delta x over 1.33 r. The focal point occurs when this refracted ray crosses the central ray. So what we want to do is we want to look at this triangle here. Okay? The triangle that goes up to the point of crossing, back to the point where the incoming ray meets the lens, and so forth. Okay? So, how can we determine the angles of this triangle? Well, I've claimed up here that this angle here is theta I minus theta r. I haven't really given a construction that shows that, but let me indicate what that construction would be. Okay, we come through here, and if we extend this line straight, then we see that I've got theta I here. Well, with the straight line, I would have an angle theta I in here. Okay? And let me actually go ahead and just indicate where that is. Okay, if we extend this line straight, there's not really anything going on there, but this angle here is going to be theta sub I. Now let's focus in on it. Okay, the angle goes from this ray to this ray. And that angle is, of course, the same as this angle over here. Okay? Now what do we have? We have the angle theta sub I here, and we have the angle theta sub r here. So that this little angle right here is what? Theta sub I minus theta sub r. It's a difference of this angle and this angle. So this angle is theta sub I minus theta sub r. If we back up, we can see that this line segment here is parallel to this one, so that this angle here has to be equal to this angle. And we just saw that this angle is theta I minus theta r, so this angle is theta I minus theta r. Having determined that, it's going to be fairly easy to determine the focal length. Okay, the big triangle that we're looking at now has the angle theta I minus theta r here, and this distance is what we're going to call f. Now remember, this triangle is the right triangle that we get from this figure. Okay, we come down to here, straight across here, at a right angle to the central ray, and then back. And f is going to be this distance here. Okay, the distance, essentially the distance behind the center where this, where the two rays cross. Now, there's a little bit of difference. Okay, if I draw the projection line straight across here, we see we've got a little bit of distance down here. So the distance from the lens back to the focal point is really a little bit more than what we're saying. But remember, we're assuming that delta x is much smaller than r, which means that this distance is going to be really insignificant. So we're going to ignore it. And we're going to say that the distance from the lens back to the focal point is the same as this side of this triangle. Okay, so this focal distance here is the side of a triangle with angle theta I minus theta r and a distance delta x here. And we see, of course, that delta x is this distance, which is this side of the triangle. Now this angle is, in radians, approximately delta x over r minus delta x over 1.33 r. We see that the focal distance, well, let's just use a little trigonometric ratio here. From this angle, the focal distance is the adjacent side where delta x is the opposite side. the opposite over the adjacent is the tangent of this angle, so that delta x over f would be the tangent of this angle. Okay? The tangent of the angle is delta x over f. If we solve this for f, we see that f is delta x over the tangent of the angle. Now, what is the tangent of the angle? Well, for small angles, the tangent is very nearly equal to the sine, which is very nearly to the angle in radians. So that the tangent of theta I minus theta r is just about equal to theta I minus theta r, which is this expression. So we replace the tangent of theta I minus theta r with theta I minus theta r in this form, and we get this. And the rest is simple algebra. Okay, we put the denominator over common denominator of 1.33r. That's going to give us 1.33r delta x minus r delta x, or actually let's say just minus delta x, over 1.33r. And inverting and multiplying, we get this. You should know how to do the algebra. Work it out yourself. Just take this expression, put this over common denominator, then invert it and multiply by delta x, and you're going to get this. Okay? And we factor the r out, or divide numerator and denominator by r, whichever way you want to look at it. We get this, and we see that we get a focal length of approximately 4r. Now let's go back to reality. Here's our sphere. We're saying that rays that come in here from this side will get bent and focus at a distance 4r from here. Well, the other side of the sphere is only distance 2r. 4r is way on the other side. It's a full diameter on the other side, so that the rays ought to focus here. Well, they would if we let the let's say we extended this half of the sphere, the back half of the sphere, out to allow the rays to actually converge. That's where they would converge. At least the rays close to the center would converge at that point, and that would be our strongest focus for parallel rays. However, we don't focus at that point because the sphere isn't big enough. And no matter what radius we make the sphere, no sphere is going to be big enough for this index of refraction, 1.33, to result in convergence within the sphere. The convergence will always be on the other side of the sphere. And we'll go on with this analysis in the next clip.